Okay, so we're going to pick up where we left off today, talking about different forms of improper integrals. Another type of integral that's considered improper has an infinite discontinuity, either at or between the limits of integration. So let's look at a picture here. Suppose we ask you to find the integral of this function from 0 to 1. If you'll notice that it has an infinite discontinuity, or really a vertical asymptote at 1, which is the right-hand limit. That's what makes this improper, because you could see that the area here would be unbounded. Likewise, take a look at this function now. So we have the integral of 1 over x cubed from -1 to 2. I want to mention also, last year when we talked about integrals and we talked about integration, one condition to be able to evaluate a definite integral was that the function had to be continuous. And the reason was because if there was a discontinuity in the middle of it, what was going on with the function, what was happening. And so this year, we're changing that a little bit and saying, if you have that infinite discontinuity in between the limits of integration, then it becomes an improper integral. Let's talk about how we would handle these cases. Okay, if f is continuous on the closed interval from a to the open interval b, and it has an infinite discontinuity at b, then we rewrite this as the integral from a to b turns into the limit as c approaches b from the left of the integral from a to c. If f has the infinite discontinuity at the left endpoint, then we'd write the integral from a to b as the limit from c to a from the right of the integral from c to b. So that time the lower limit gets changed, but we approach it from the right. And in the last case, if we have an infinite discontinuity inside of the interval, then we have to break it up into two separate integrals, similar to the ones we did yesterday where we went from negative infinity to infinity. So the integral from a to b turns into the integral from a to c. We would evaluate it using this one-sided limit we had up here, plus the integral from c to b, and we would evaluate that using this one-sided limit here. Okay, so let's take a look at this example. So we have the integral of this function, the square root of 1 plus x over 1 minus x. And as we said earlier, there's an infinite discontinuity at x equals 1. So we're going to define this, we're going to rewrite it as the limit as c approaches 1 from the left from 0 to c. So since that discontinuity was the right endpoint, we approach that limit from the left side, from the inside of the interval. Okay, so to evaluate this, it was a little bit unconventional, but what we're going to do, and there may have been another way to do this, but what I did is I went ahead and I rationalized the numerator. And I wrote it as the integral of 1 plus x over the square root of 1 minus x squared. I'm going to break this into two separate integrals. The first one you'll see is an arc sine, but the second one requires a u substitution. So when we find that antiderivative in terms of u, go back and change it to in terms of x. And remember, we were integrating this from 0 to c, so we still have to apply the fundamental theorem of calculus. We have arc sine of c minus the square root of 1 minus c squared minus arc sine of 0 minus the square root of 1. So as c approaches 1, just think direct substitution. Arc sine of 1 was pi over 2. 1 minus 1, of course, is going to be 0. Arc sine of 0 is just 0, and then we're just left with pi over 2 plus 1. So this integral, we would say, converges to the value pi over 2 plus 1. Now let's look at this function. We have the integral of 1 over x from 0 to 1. Take a minute and think about why this would be considered an improper integral. You'll notice that there's a discontinuity at the left endpoint this time. We're going to rewrite this as the integral from c to 1 as c approaches 0 from the right. So now we're approaching it from the inside of the function from the right. So the antiderivative is natural log of x. Evaluating it from c to 1, we have the natural log of 1 minus the natural log of c. You could evaluate these separately. In the PowerPoint, I went ahead and I condensed this and wrote it as the natural log of 1 over c. And think about, as c approaches 0, this approaches infinity. And as x approaches infinity, the natural log of that would approach infinity as well. So what does that mean for the improper integral? We would say that it diverges because there's really no limit here. Next example, so we have the integral from 0 to 3 of this function. Think about what would make this improper. We have an infinite discontinuity at x equals 1, which you'll notice is in between the limits of integration. So first I just rewrote the integrand. Then we're going to break this up. So we're going to write it as two separate integrals. Make sure you see what we're doing. So now we have the limit from 0 to c as c approaches 1 from the left. So that would be covering the left half of this area under the curve, plus the integral from c to 3, so pick up where this one leaves off, as c approaches 1 from the right. So that would be the right half of this integral. We have our antiderivative. We're evaluating from 0 to c for the first one and c to 3 for the second one. Using a little bit of direct substitution, we get this. First one goes to 0. The last term there goes to 0. And since we're left with a number, not a pretty number, but we're left with a number, that means the integral converges to this area. Okay, last example. So this one's a little bit more abstract, but I want you to think about the cases here. So we have the integral from 1 to infinity of 1 over x to the p, and p is a number greater than 0. So remember, p is a constant here. I'm going to rewrite this as x to the negative p. Of course, this is a power rule. The antiderivative for this is just 1 over negative p plus 1 times x to the negative p plus 1. We're evaluating this from 1 to b because I made my limit as b went to infinity. Now keep in mind, x is where you're going to put these limits of integration. P is a constant, that doesn't change. So when we use the fundamental theorem of calculus on the x, we have negative b to the p plus 1 over negative p plus 1 minus 1 to the negative p plus 1 over negative p plus 1. So what I want you to think about here is what's going on with the various p values. If this negative p plus 1 turns out positive, then as b goes to infinity, this first fraction will blow up and go to infinity. So in order for that to turn out positive, p has to be less than or equal to 1. Make a little inequality on your paper so you see it. Negative p plus 1 greater than 0. In that case, the integral would diverge. On the other hand, if this exponent turns out negative, it sends this b to the denominator. So as b goes to infinity, what would happen in that case to this fraction? It would go to 0, and the whole thing would converge to this fraction over here. I want you to remember this example because when we get to the next chapter, you're going to see these two cases again in a similar problem.